We've seen some consequences of compactness, but there's a very nice interplay, especially with compactness and metric spaces. So that's what we'll see in a few examples of. So first of all, let's look at a definition. A metric space XD is complete if it has no holes in a metric sense. That is, if every Cauchy sequence in X is convergent. Now, since metric spaces are not a prerequisite, even though you can guess the definition of this, we will still say, I'll just spell it out, Xn is Cauchy if for all epsilon greater than 0, there exists n greater than 0, such that if you have two numbers n m bigger than m, the distance between xn and xm is less than epsilon. So far enough points are close to each other, and completeness tells you there should be a limit. So rational numbers are not complete because you could have a sequence going to square root of 2 or pi or something, which would be Cauchy, but it would not be convergent. Okay, and so the theorem here, so what leads to completeness? The converse of this is not true, but one way you can conclude completeness is if X is compact as a topological space, then X is complete. Okay, so proof is, let's assume X compact, and assume that we have a Cauchy sequence, Xm Cauchy. Okay, then some subsequence Xn k is convergent. Okay, say to X infinity, where without loss of generality, let's assume nk is greater than or equal to k for all k. So subsequence, well, its definitions of subsequence differ, but you could take this as part of the definition, or if not, just can assume this without loss of generality. So we have a subsequence which converges, and then the claim is that in fact Xn converges. Xn converges to, well, without loss of generality, let me assume more than this. So without loss of generality, nk is increasing. So we have a strictly increasing sequence of indices. When we talk about subsequences, this converges to C. Claim is that Xn converges to X infinity, and of course we prove it using the subsequence and Cauchy property. So let epsilon greater than 0 be given. Okay, as Xnk converges to X infinity, there exists, let's say, n prime greater than 0, such that k is greater than n prime implies that distance between x and k and x infinity, I was going to say, is less than epsilon, but we have to give ourselves some room. So let's call it epsilon by 2. Okay, and as xn is Cauchy, there exists another quantity n double prime greater than 0, such that n and m greater than n double prime implies that xn, distance between xn and xm, is less than epsilon by 2. Now we simply have to put these two together. And in fact, if n is greater than n double prime, okay, so we find nk such that, find k such that nk is greater than both n and n prime, So max of n in n prime. Okay, so the subsequence term is very far out. N is also bigger than enough for the Cauchy term. Okay, so then what we know is that the distance between xn and x infinity, this is less than or equal to distance between xn k. The Cauchy term controls that, and the fact that nk is big enough and the convergence of the subsequence controls the second thing, xn k, and x infinity. So this is less than epsilon by 2 plus epsilon by 2, which is epsilon. Okay, so this is where we are done. So this was our first consequence. We'll look at another basic consequence and then leave for the next segment a deeper result. Okay, so the next simpler consequence is the following. It's called the Labeg number theorem. This tells you that not only do you have a finite subcover, but we have a subcover which is kind of nice. We have a better control of that. Okay, so let X be a compact metric space. Oh, I omitted to say one thing here. Okay, well, why does it have a convergent subsequence? I mean, it's because it's compact. It's sequentially compact since every metric space is first countable. Yeah, so that's what we used already, and we'll use these kinds of things again and again. So X is a compact metric space. So let X be a compact metric space, and theorem: if U alpha, so if I have an open cover of A, is an open cover of X, there exists epsilon greater than 0 such that if A is contained in X and diameter of A is less than epsilon, then there exists alpha naught in A such that not in A was a bad choice here. Let me just call it Y is contained in X with small enough diameter. Then there exists an index such that Y is contained in U alpha naught. So it's not merely that you have a finite subcover. Finite subcovers could sort of intersect with a small overlap, but in fact any small enough set is contained. There's some uniform number, so that depending only on the cover, so that a small enough set is contained in one of them. This becomes very useful in various spaces, including in covering space theory. So idea is that suppose not, then for all n, we'll take epsilon as 1 over n. So for all n greater than or equal to 1, there exists Y contained in X such that diameter of Y is less than 1 over n, Yn. So let's call these Yn, and the diameter of Yn is contained in 1 over n, and Yn is not contained in a single U alpha, in U alpha for all alpha. It's not contained in a single set. Okay. So now pick points. Let's call them little Yn, and Yn. So the sequence Yn, again, because of sequential continuity, has a convergent subsequence. Okay, so Ynk. So that is, what we know is Ynk converges to Y infinity, and diameter of the sets Y and K go to 0. Actually, this is enough for the contradiction. We'll ignore the rest of the Y and K's. That is, Y and K converges to Y infinity. Okay, but what do we know? But Y infinity is in X, so there exists alpha naught such that Y infinity belongs to U alpha naught. Okay, hence Well, this is open, so it has an open ball around y infinity. So there exists eta greater than 0 such that ball around y infinity of eta is this ball contains is contained in u alpha naught. Now what's the situation here? We have the point y infinity. We have a ball here of certain radius, and it's contained in one single open set u alpha naught. Okay. But now what happens is the diameters of these sets become smaller and smaller, the sets y and k. Okay, so for nk large enough, for k large enough, what do we have? We have distance between y and k and y infinity. This is tiny, is less than eta by 2. So a point in the kth set, and the diameter of this and diameter of y and k is less than eta by 2. Hence, from definition of diameter, you conclude that y and k, so all points of y and k are contained. So you are contained in half the ball, and your diameter is less than half the radius of the ball. Hence, you see that y and k is contained in ball y infinity of eta, and which is contained in u alpha naught. But this is a contradiction, because we found smaller and smaller sets which allegedly were not contained in, which so our assumption was that these were not contained in a single cover. So that is impossible. So by contradiction, we conclude that there was actually u alpha which covered, so there is actually an epsilon, so that any set smaller than epsilon is covered by a single one of these given open sets.